I followed the interview guidance material which was given to me as a part of ACE Online's interview guidance program.
I am Vinit Kumar. I have secured All India Rank 1 in Mechanical Engineering in ESC 2020.
Hi students, so I'm back again. So I think in my last video, I have given some preparation strategies for ESC and GATE. So hope my students, my dear students, I think you'll be following that. Now let us see some very important concept. So before to that, as you are aware, myself is Dr. Abdul Ahad, right? So I'm trying to take some important concepts in induction machines. So you know that machines is a big ocean. So instead of boiling the machines, we are going to take a bucket of water, we'll boil it like that. Bucket we are going to boil now. It is something like. So honestly speaking, it is not possible to boil the entire ocean. So just we are taking a small topics and we are going to complete, right? So I'm trying to take a important topic in this. So before we are trying to take the important topic in this induction machine, so let us see your syllabus for engineering service as well as GATE. So basically it is like into main parts. So here we need to discuss the concept of rotating magnetic field, the construction of an induction machine, the complete working principle, the steady state analysis, that means finding out the performance parameters of an induction motor, representing the machine electrically like an equivalent circuit, using that equivalent circuit, finding out the complete performance parameters and drawing the torque slip characteristics of a induction motor. We discussed that under steady state analysis. After that, the starting methods, speed control techniques, testing, harmonic analysis, and single phase induction motor. So roughly, so these topics are from your syllabus. Now as I told you that I am trying to take a small bucket of water and I want to boil it, and I am trying to take a small topic and trying to explain that. So which topic I am trying to explain means starting methods, right? So let us take a starting method. Right. So starting methods, very important. First, why starters are necessary for a three-phase induction motor? We are aware that a three-phase induction motor is basically a self-starting motor. But still, a three-phase induction motor need a starter. But as the name says, the purpose of starters for a three-phase induction motor is not for starting a three-phase induction motor, but it is to limit the high starting currents. Why? Because you know that a three-phase induction motor is a self-starting motor. How? Just if I am trying to just brief out. So whenever we give a three-phase supply to the three-phase stator windings, which are spaced at an angle of 120 degrees, then we have a rotating field. So this rotating field cuts the stationary rotor conductors and an EMF is induced. Then the induced EMFs in the rotor windings or the rotor conductors will establish as a current. Because of these rotor windings and rotor currents, induced current, there will be one more field, that is the rotor field. The stator field and the rotor field will interact and they make the rotor to rotate. So finally, a three-phase induction motor is a self-starting motor. But why still a three-phase induction motor need a starter means, as the name says, is not for starting the motor, it is to limit the high starting currents. Now we are trying to see why a three-phase induction motor will draw high starting currents. Just give me a minute. Why it will try to take or why it will try to draw high starting currents. Right? I'll try to explain that. Right. So why a three-phase induction motor draws high starting currents? I'll try to take a circuit. The rotor equivalent circuit. A rotor equivalent circuit. I am trying to explain why a three-phase induction motor will draw high starting currents. I am trying to take a rotor equivalent circuit when the motor is operating at a slip of S. I think you people are aware of this circuit. So this is the rotor winding resistance, this is the leakage reactance, and this is the load impedance. And this is E2 naught. This is I2. So this is the equivalent circuit of a rotor when it is motor is operating at a slip of S. If you take any induction motor, the rotor winding resistance R2 will be very small. The value of R2 will be very small. The reason why the resistance should be very small or very less means the performance of an induction motor depends upon the losses. If the losses are more, the efficiency of the motor will be less. The losses in the induction motor will be the losses in the stator winding, the losses in the rotor winding, and that losses in the windings will be due to that winding resistance. So if you want to have a higher efficiency motor, the winding resistance should be very less. So that is the reason whatever the material we are selecting for the rotor winding should always have a low resistance. So generally for any induction motor, the R2 value will be very, very less. Why? Because more R2 will have more losses. As a result, the efficiency will be less. Because of losses, the temperature will be high, windings will get damaged. So for that, we have the rotor resistance always very small value. Let us consider in one induction motor, the value of this resistance is say 0.12. The other one is the leakage reactance. This leakage reactance at standstill should be again a smaller value. Why it should be smaller means, as you know that if the leakages are more, the leakage reactance will be more. If the leakage reactance is more, then obviously the power transfer to the rotor circuit will be less. If the power transfer to the rotor circuit active power is less, the torque which depends on that will be less. So that is the reason always we need to have lesser leakage reactance. More leakages will transfer less power, less leakages will transfer more power to the rotor. So for more torque, the rotor should receive more active power. For that, the leakages should be less. So the leakage reactance will be less. So let us consider in our case, the leakage reactance is 0.85 ohms. Let us take generally. Right? So whatever the induction motor we have considered, so let the rotor winding resistance be 0.12, the leakage reactance at standstill be 0.85. So this is the rotor equivalent circuit at any slip. Now if I am talking at starting, what is the value of NR? At starting, the value of NR will be 0. So before to that, what will be the equation for the rotor current here? Equation for the rotor current is E2 naught by square root of R2 plus R2 into 1 by S minus 1 whole square plus x2 naught whole square. This is for this circuit. Now let me talk at starting. At starting, NR is equal to 0, slip is equal to 1. When slip is equal to 1, R2 into 1 by S minus 1 will be 0. Then if I try to draw the rotor equivalent circuit, you can see the rotor equivalent circuit at starting will be like this. At starting will be like this. You can see this will be a dead short circuit. This is E2 naught, this is R2, this is x2 naught, this is I2 start. If I try to write the equation for I2 start is equal to E2 naught by square root of R2 plus 0 whole square plus x2 naught whole square. You can see during starting which branch is not present in the rotor circuit, the load impedance. So which one is the load impedance here? R2 into 1 by S minus 1 is the load impedance, and that branch is becoming 0 at starting. As there is no load impedance here, you can see as this load impedance is absent in the rotor circuit, as the values of R2 and X2 naught are very small, this rotor impedance will be very less. Why? Because I told you that R2 and X2 naught for any induction motor will be very less, and hence this rotor impedance will be less. As a result, the rotor ohmic losses will be more. When the rotor rotor current will be more. When the rotor current is more, the rotor ohmic losses will be more. Then if I neglect the no load current, then the stator current will be this one. So as the stator current is more, the stator ohmic losses are also more. The losses in both the windings will be more. The temperatures will be high. Because of high temperature, the insulation will get melt. When the insulation get melt, obviously the windings and windings, conductors and conductors will short, and windings will get damaged. So windings will get damaged. So who is the main culprit for high starting current? Means the load impedance. The load impedance R2 into 1 by S minus 1, who is supposed to present in the rotor circuit, that fellow is not there in the rotor circuit at starting. Why that fellow is not there in the rotor circuit at starting means, as you can see, NR is equal to 0, slip is equal to 1, the load impedance will be 0. As the load impedance is 0, as R2 and X2 naught values are very less, the rotor impedance will be less, the rotor current will be high. As the rotor current is high, the rotor ohmic losses will be high. Due to this high rotor current, stator current will be high, stator ohmic losses will be high, then the losses in both the windings will be high, the temperatures will be high, the insulation will melt, and windings will get damaged. So finally, who is the main culprit for this? High starting current means the load impedance R2 into 1 by S minus 1 is not present in the rotor circuit during starting. Sir, how the winding currents are normal during running conditions? For example, sir, during running conditions, if say the motor is operating at a slip 4%, then what is the value of slip? S will be 0.04. Then if I calculate the value of load impedance R2 into 1 by S minus 1, so this will be roughly 2.88 ohms. So can I say during running condition, even though the values of R2 and X2 naught are very less, as this load impedance is present in the rotor circuit, the overall rotor impedance will be high, the rotor currents will be less, stator currents will be less, the ohmic losses in both the windings will be less, the temperatures will be less, and windings will be safe. So like that, the motor windings are being protected during running condition. But very unfortunately, which fellow or which branch is absent in the rotor circuit at starting means the load impedance. Why that fellow is absent means, as at starting NR is equal to 0, slip will be 1, R2 into 1 by S minus 1 will be 0, the overall rotor impedance will be less. As the rotor impedance is less, the rotor current will be high, the stator current will be high, the ohmic losses in both the windings will be high, the temperatures will be high, the insulation will get damaged, the windings will get damaged. So this is for starting. But during running condition, even though the values of R2 and X2 naught are very less, as the motor is operating at some slip, yes, the load impedance is present in the rotor circuit. Because of this load impedance, the overall rotor impedance will be high. As overall rotor impedance is high, the rotor currents will be less, the stator currents will be less, the ohmic losses in both the windings will be less, the temperatures will be less, and windings will be safe. Right? So during running condition, this load impedance is like safeguarding the windings. Now my question is, sir, we agree with respect to equation, but what is the real mechanism? Now let us assume this is a 6-pole induction motor. Just one second. no problem. So let us assume this is a 6-pole induction motor. 6-pole induction motor excited with a 50 hertz supply. Then what is the synchronous speed? Ns is equal to 120 into 50 by 6. How much it is? 1000 rpm. The field speed is 1000 rpm. At starting, what is the value of Nr? Nr will be 0 at starting. As Nr is 0, what is the relative speed? Relative speed between stator field and the rotor conductors. It is Ns minus Nr, that is nothing but Ns. So at starting, the relative speed between the stator field and the rotor conductors is Ns, that is, it is very large. So due to this large relative speed or more relative speed, that is Ns minus 0, then the stator flux lines will be cutting the rotor conductors more number of times. Because of that, EMF induced in the rotor conductors will be more. Then currents in the rotor conductors will be more. Current drawn from the stator conductors will be more. The current drawn from the supply will be more. Then ohmic losses in both the windings will be more. Temperatures will be high and windings will get damaged. So in two ways we can explain, in two ways. What is the first way? At starting, Nr is equal to 0, slip is equal to 1, the load impedance R2 into 1 by S minus 1 is not there in the rotor circuit. As a result, the overall rotor impedance is less, the rotor currents are high, the stator currents are high, the ohmic losses in both the windings will be high, the temperatures will be high and windings will get damaged. In other way, without the equation, with some concepts I can say, at starting, rotor is stationary, rotor conductors are, rotor windings are stationary, but the field will be rotating with a speed of Ns. Then the relative speed between the stator field and the rotor conductors will be Ns minus 0. It is Ns, then the flux cutting the rotor conductors will be more, EMF induced in the rotor conductors will be more, currents will be more, ohmic losses will be more. Similarly, in the stator also, the currents will be more, ohmic losses will be more, then temperatures will be high and windings will get damaged. So this is the reason why the starting currents will be very high. Then what happened to during the running condition? During running conditions, say the rotor is rotating with a speed of 960 rpm. Then what is the relative speed? Relative speed, it is 1000 minus 960, it is 40 rpm. You can see the relative speed between the stator field and the rotor conductors is very less. Flux cutting the rotor conductors are less, EMF induced in the rotor conductors are less, currents in the rotor conductors, currents in the stator winding are less, ohmic losses will be less and hence the temperatures will be less and windings will be safe. So if you feel the difficulty in explaining with respect to equation, then I can say with respect to relative speed, at starting the relative speed between the field and the rotor conductors is more, flux cuttings will be more, currents will be more. But during running condition, as the rotor is rotating, the relative speed between the stator field and the rotor conductors will be less and hence the EMF induced in the rotor conductors will be less, currents drawn from the supply will be less, ohmic losses will be less and windings will be safe. So finally, can I say like this, the purpose of starters for a 3-phase induction motor is not for starting a motor but to limit the high starting current. So the main purpose of starters for a 3-phase induction motor is to limit the high starting current. So magnitude wise, these starting currents will be 5 to 8 times the full load current. If such high current flows in the motor winding, what happened to the windings? Damages. Now let us see how to control such high starting current. Why? Because high starting or high inrush of current are not safe for the motor windings or motor. So we need to limit such high starting current. How to control such high starting currents? Let us see. If you see this starting current equation, rotor current, I start is equal to E2 naught by square root of R2 plus 0 whole square plus x2 naught square. So by looking into this equation, one can say that the starting current can be controlled by E2 naught, by rotor circuit resistance, or by leakages. Now if I take a slippering induction motor, you know that in case of a slippering induction motor, we have the provision of adding an external resistance in the rotor circuit. By adding some external resistance, so we are not adding this external resistance to control the current, but you people are very much aware. So in case of a slippering induction motor, by adding some external resistance, you are making the circuit highly resistive. When you are making the circuit highly resistive, the rotor power factor will be high, the active power drawn from the source and the rotor will be high, the torque which depends on that will be high. That means the starting torque will be very high. So to improve the starting torque, in case of a slip ring, we are adding some external resistance in the rotor circuit. So whatever that external resistance we are adding in the rotor circuit to improve the starting torque, it is not only improving the starting torque, even with that external resistance, we can increase the rotor impedance and hence we can decrease the rotor current also. So in case of a slippering induction motor, we don't need any external starters to control the starting current. Why? Because whatever the resistance we are adding in the rotor circuit, that resistance itself will control the starting current drawn from the supply, and hence we don't need any external starter for a slippering induction motor. But whereas in case of a squirrel cage induction motor, you know that in case of squirrel cage induction motor, we don't have the provision of adding or changing the rotor circuit parameters. Why? Because in case of squirrel cage, the rotor bars are permanently shorted with end rings. We don't have the provision of varying or changing the rotor circuit parameters. So if you look into this, so in case of a squirrel cage, the only one parameter by which we can change or control the starting current is E2 naught. So this E2 naught is equal to E1 by E1 by A sorry, somewhere, no problem. So I'll take that equation once again. So it is gone, just technical issue. So if you take the rotor current at starting, it is E2 naught by square root of R2 plus 0 whole square plus x2 naught square. So here this is equal to E1 by A, and that is equal to V1 by A. V1 by A. So by looking into this equation for a squirrel cage induction motor, as you can see, in case of squirrel cage induction motor, we cannot change this rotor circuit parameter. So the only one parameter by which we can control the starting current is by changing E2 naught value, that is the rotor voltage at starting. So if I want to change this E2 naught value, then I have to change E1, then I have to change V1, where V1 is nothing but the supply voltage. Supply voltage. So in case of a squirrel cage induction motor, if you want to control or if you want to limit the high inrush of starting current or high starting current, you need to start the motor with reduced voltage. You need to start the motor with reduced voltage. So by starting the motor with reduced voltage, E1 can be reduced, from that E2 naught can be reduced, by that I2 start can be reduced, from that I1 start can be reduced, the currents in both the windings can be reduced. So how you are going to control such high starting currents means by starting the motor with reduced voltages. Reduced voltages. So it is possible in case of which motor? Squirrel cage. Why? Because in case of slippering it is not required. So in case of a squirrel cage, if you are going to control the high starting current, we need to start the motor with reduced voltages, right? But what is the main problem with this means we need to sacrifice some of the starting torque. Why? Because you people are aware that the starting torque is directly proportional to voltage square. If you are going to start the motor with reduced voltages, the starting torque will reduce. That means when you are controlling the high starting current, we need to sacrifice some of the starting torque. But you may have a doubt, sir, a squirrel cage induction motor is having poor starting torque. Now you are trying to say that by starting the motor with reduced voltage, we need to sacrifice some of the starting torque. Does it affect the performance? Generally, no. The reason is the squirrel cage induction motors we are using for raising loads like fan loads, mixer loads. So the starting torque requirement for such loads will be very less. Even though we are starting the motor with reduced voltage, the torque is enough to drive the load. But once the motor starts rotating, we should not keep the voltage low. Once the motor starts rotating, then we need to increase the voltage and we need to operate the motor with rated voltage. Why? Once the motor starts rotating, the relative speed between field and conductors will decrease, flux cutting the rotor conductors will decrease, currents in the rotor conductors and the stator conductors will also decrease, windings will also decrease. So there is no need to operate the motor with reduced voltage. Once the motor starts rotating, we need to increase the voltage and finally we need to apply the rated voltage, right? So this is something about your squirrel cage motor. So finally, can I say like this? Why starters? Why starters? Can I say like this? Can I say like this finally? So why starters? So why starter is necessary for a three-phase induction motor? I can say the purpose of a starter for a three-phase induction motor is not for starting the motor, as a three-phase induction motor is a self-starting motor. But the purpose of starter is to limit the high inrush of starting current. Why the motor will draw high currents during starting? The reason is the load impedance R2 into 1 by S minus 1 is 0 at starting. As a result, the overall rotor impedance is less, the rotor current is high, the stator current is high, the ohmic losses in both the windings are high, the temperatures are high, the windings will get damaged. In other way, at starting, as NR is 0, the relative speed between the stator field and the rotor conductors is NS more, flux cutting the rotor conductors will be more, and hence EMFs will be more, currents will be more, ohmic losses will be more, and hence the windings are prone to damage. So to limit that, we need a starter. But why not in running condition? In running condition, the relative speed will be less, flux cutting the rotor conductors will be less, EMF induced in the rotor conductors will be less, currents will be less, ohmic losses will be less, and temperatures will be less, windings will be safe. In other way, the load impedance is present in the rotor circuit during starting, during running. Why? Once the motor starts rotating, NR will increase, slip will decrease, R2 into 1 by S minus 1 will build up, which increases the rotor impedance, and hence the currents will be less. So during running condition, we don't need any starters. Then how to control such high starting current? So in case of slippering induction motor, whatever the resistance we are adding in the rotor circuit to increase the starting torque, that resistance itself will control high starting current. But whereas in case of a squirrel cage induction motor, it is not possible. So in case of a squirrel cage induction motor, compulsorily we need an external method to control such high starting current. For that, we need to start the motor with reduced voltage, right? But we need to sacrifice some of the starting torque, right? So can I say a starter is necessary to limit this starting current to avoid the damage to the motor as well as the other adjacent equipment. The other one is a starter is a device that reduces the initial high currents of the motor by reducing the supply voltage applied to the motor. So with the help of this starter, we need to reduce the voltage what we are applying to that motor, right? Now what are the different types of starters, right? So basically the starters are classified into two, the full voltage starters and reduced voltage starter. So full voltage starter means, so using these starters, we are going to start the motor directly with rated voltage. So as I told you that with rated voltage, the windings will draw very high currents, but these DOL starters, which comes under the category of full voltage starter, so we are using this for low HP motors. So even though we are going to start the motor with rated voltage, even though the windings are carrying the currents 5 to 8 times of the full load current, still the windings will be safe in this case. Why? Because such high currents will be flowing only for short time. Why? You can see in detail in dual starting methods, right? Done. The next one is reduced voltage methods. In case of this reduced voltage method, we are going to start the motor with reduced voltages, right? So what are the techniques means? One is the stator reactors or resistance starting method, auto transformer starting. So there is a correction, starting, some T is missing here. Starting, star delta starting methods, right? So basically the starters are classified into full voltage and reduced voltage. In full voltage, we have DOL starter. In reduced voltage, we have these 3 starters, right? Please. Now let us talk one of the method, series reactors or resistor starting method. What is the logic in this? What is the logic in this? I'll try to explain the basic logic. Basic logic. So I'm not going to discuss everything in detail, just basic logic so that you can understand. So assume that this is the motor with a impedance of Z01. In case of this, series reactor or resistor starters, what I am trying to do means I am trying to connect reactors in series with each line. In series with each line. In series with each line. Like this. In series with each line. So let me explain what is the importance of this. Say, if I am applying a voltage of 100 volts per phase here, if I am applying a voltage of 100 volts per phase here, so here in the series reactors, say I am dropping some 10 volts. Just I am taking some arithmetic value. I am dropping some 10 volts. So out of these 100 volts, 10 volts I am dropping here. Then what is the voltage I am applying across each stator terminals here? 90 volts. 90 volts. So here you can see that whatever the voltage you are applying across this 3 phase, we are not giving the same voltage here. So a part of the voltage is dropped in the series reactor and the remaining voltage is applied across the stator winding. So instead of like this, I'll try to tell, see if it is the if I am applying a per phase voltage of say V, if I am applying a per phase voltage of V, let us assume there is some voltage dropped here and what is the voltage I am applying here? XV. So where X is a percentage tapping here, so X is less than 1. For example, say X is equal to 0.9. What is the meaning of 0.9 means? So out of 100%, so 10% is dropped here, 90% is applied here. So we are reducing the voltage that we are applying to the stator winding by some 10%. If say X is equal to 0.5, so 50% we are dropping here, 50% we are applying here. So 50% is dropped. So using this series reactors, a part of the voltage that is applied to the motor windings or the stator windings is reduced. As you remember, starting currents are directly proportional to the supply voltage. If the supply voltage is reduced, the rotor current will be less and hence the current drawn from the stator will be less and hence the losses in both the windings will be less and hence the temperatures will be less. Please try to understand the fundamental. We have some equations relating to that. So how much is the percentage of current reduced, how much is the percentage of torque reduced, that is a different task which we can discuss in detail right later. But here my intention is how to control such high starting current means by starting the motor with reduced voltage. By starting the motor with reduced voltage. So one of the method to start is with the help of a series reactor. In case of the series reactors, what we are trying to do, a part of the voltage is dropped in the reactors and the remaining voltage is applied across the stator winding. As the voltage what we are applying to the stator winding is reduced, the starting current will also reduce. So like that, in case of a variable reactor starter, we are going to reduce the starting current like this. But what is the main problem with this is, so here the reduction in the current will be X. But if you take the starting torque, starting torque is directly proportional to V square. So starting torque is directly proportional to X into V square. So here X square into V square. So current is reduced by X time. So if I take current, starting current, it is X into V by Z. So it is X into ISC. So the current is reduced by X times, whereas the torque is reduced by X square time. So for 10% reduction in the current, we need to reduce 20% torque. We need to sacrifice more amount of torque in these variable reactor starters. So one more problem we are having with this variable reactor starter is this three-phase induction motor is a single excited machine. For example, say if I am calling myself as a source, if I am supplying active power and also reactive power, my power factor will be less than 1. Why? Because I am the source who is supplying active power, at the same time reactive power. If both active power and reactive power are supplied from me, my power factor cannot be equal to 1. It will be always less than 1. As you take an induction motor is a single excited machine. So whatever the reactive power that is required to produce the field, whatever the active power that is required to produce the torque will be drawing from the same source. So here the source is supplying active as well as reactive power. As a result, the power factor of an induction motor will be always lagging. It can never be equal to 1. But whereas in case of a synchronous motor, if you remember, the power factor can be unity, lagging or leading. Why? Because it is a double excited. So here in case of a synchronous motor, even from the rotor side also we can supply the reactive power. For example, say by increasing the field or by field current, if you are not able to supply the required reactive power to produce the field, then the stator will draw the reactive power. In that case, the synchronous motor will operate as a lagging power factor. Why? Because the rotor circuit is not supplying the required reactive power to produce the field. The stator is supplying. If the rotor is supplying the required reactive power, then the stator will not supply any reactive power. The power factor will be 1. If the rotor is supplying more than required, then the additional power will be supplied to the source. It will be leading. So in synchronous motor, we can have lagging, leading as well as unity power factor. Why? Because from the rotor side, we can control the power factor. But whereas in case of an induction motor, it is not possible. Why? Because it is a single excited machine. The required reactive power to produce the field, it will draw from the stator side, and hence the power factor will be always less than 1. In addition to that, you are connecting a reactors here. A reactor also need a reactive power. So for that, they will draw from the source. As a result, what happened to the overall power factor? Decreases. So what are the main two problems we are having this with variable reactor starter or stator reactor? Means the current will be reduced by X time, but the torque will be reduced by X square time. So these starters cannot be used for high starting torque requirements. The other one is because of this series reactor, the source has to supply more reactive power. As a result, the power factor of the source will be less. So to rule out that problem, we are replacing these reactors with resistors. So resistors may try to improve the power factors, but because of the resistors, the ohmic losses will be more, and hence efficiency during starting will be less. So this is something about a brief introduction, a very brief introduction about the series reactor starter. So there are many equations to be discussed, so everything we'll discuss in detail in our regular classes, right? I hope you understood this. So yesterday we have discussed the preparation strategy. So please try to make a timetable according to the number of days available, and try to make a timetable and try to start your preparation. And we'll have a subject, as I told you, that we cannot boil the entire water at a time. We have to take a bucket of water and boil so that we can get whatever it is. So here, even though the syllabus is very large or huge, don't worry with the huge syllabus. Take a small topic at a time. Try to complete the whole syllabus. I hope you understood, right? I wish you all the best, right? Take care.
Hello everyone, my name is Karthikeya Kaushik and I have secured All India Rank 1 in UPSC Engineering Services Examination 2021 from Civil Engineering discipline. For prelims preparation, I took online test series from ACE online platform and used to regularly solve their subject-wise test and full-length test. Then for mains preparation, I solved question banks which were given to me as a part of mains postal program from ACE Online. And then last but not the least, for interview preparation, I followed the interview guidance material which was given to me as a part of ACE Online's interview guidance program.
I am Vinit Kumar. I have secured All India Rank 1 in Mechanical Engineering in ESC 2021. I have been associated with ACE Engineering. I have taken various programs like Lives, main classes, postal study course, test series and interview guidance program. So would like to thank all the faculties of ACE. It has helped me in building my concepts and having my fundamentals cleared. I would also like to highlight that in test series, I have given various mock tests which have helped me in the time of real exam, and in interview guidance program, building confidence in front of interview panel. It has helped me in my success.
Myself Abhishek Kumar Sharma. I have scored All India Rank 1 in UPSC Engineering Services Examination 2021 in Electrical Engineering discipline. Now I divide my preparation strategy into three basic things. The first thing is that you have to complete your syllabus from a basic standard source. The second thing is that you have to attempt previous year question. The third thing aspirant has to do is to solve as many test series as possible. I made 2 to 3 pages short notes of each and every subject. Now 2 to 3 pages short notes help in quick revision. If you keep working hard, you will definitely get success in this examination. This is what I followed, and I wish all the best for all the future aspirants. Thank you.
My name is Kuldeep. I have done my BTech from Ambedkar Institute of Technology, which is situated in Delhi, and I have secured All India Rank 1 in ESC 2021 from E&T branch. I took ACE postal course, mains test series and interview guidance program in ESC 2020 and ESC 2021.